All right, so in this video, we're going to talk about the second derivative test, which is going to help us find the same information as the first derivative test, but just in a slightly different way. So before we actually talk about the second derivative test, we're going to talk about something called the concavity of a graph, which is something you probably haven't really talked about before, but is something you've definitely seen before a lot. So a graph is concave upward. When the derivative is increasing. So the rate of change has its own rate of change. And so this is the derivative of the derivative, right? So the derivative of the derivative. And that means that f double prime of x is positive on an interval. And concave down when the derivative is decreasing. And since this makes sense with the derivative is increasing, the derivative is decreasing, that means that the slope of the derivative would be positive. And here the slope of the derivative would be negative, because that's what increasing and decreasing actually mean, is that you have a positive slope or a negative slope. So a point of inflection is where the function changes concavity. So that's where the second derivative equals 0. So if we're still thinking of this kind of in terms of those rectilinear motion problems, what we're learning about today is kind of like the acceleration portion. So the first thing we talked about was like the velocity, the first derivative, and moving left and right and stuff like that. That's what we could relate it to. This we can relate back to kind of like acceleration and how that works. So I'm going to draw a couple sketches so that you guys can see concavity and points of inflection. So right here is the point of inflection, POI. This part right here is concave down because it's like an upside down U shape. So concave down right here. This part right here is concave up. So, and then the point of inflection is where you switch from concave down to concave up. So whenever you're looking for concavity, you're going to think of like U shape or like a bowl shape, and whether it's right side up or upside down. So, and they're not always like the whole shape. We could look at a graph like a cubic graph. This part right here is concave up. Then we have the point of inflection, and then this part right here is concave down. And I don't have the whole U shape or the whole bowl shape, but I have half of it. That part is concave up, concave down, right? We also have, maybe if you're looking at a rational function, if you're looking at something like this, that would be concave up. It wouldn't have a point of inflection because it didn't switch. So just keep that in mind. You've seen all sorts of concavity as you've graphed different things, but you haven't really recognized them or pointed it out before. Okay, so we're going to go ahead and we're going to find concavity based on the problem that we actually looked at in the first derivative video. So I'm going to write down that problem again. That was x to the fourth minus 4x to the third plus 2. And we'll go ahead, got to find the first derivative. 4x to the third minus 12x squared. And we're going to pass right over the first derivative. We're going to go straight to the second derivative. So that's going to give us 12x squared minus 24x. And then it changes concavity. It has a point of inflection where the second derivative equals 0. And so I'm going to go ahead and take this derivative and set it equal to 0. And that's quadratic, so I do need to factor to solve that. So I have a GCF of 12 and x. I can go ahead and take both of those out. So 12x squared, if I take out a 12x, then I have an x left over. 24x, if I take out a 12x, I have a negative 2 left over. So that means that x equals 0 and x equals 2 are my points of inflection. So I'm going to go ahead and draw a sign chart again. And so I need to pick numbers. I'm going to use like -1 and +1 and 3. So if I put -1 in here, I'm going to have a negative times a negative. So that means that from -infinity to 0, the graph is concave up. Plug in 1, that's positive times negative, so that's concave down. And then positive and positive, so concave up again. So concave up from -infinity to 0, and 2 to infinity. Concave down from 0 to 2. The points of inflection are at 0 and 2. And so I need to plug 0 into the original function, and I need to plug 2 into the original function to figure out what the y-coordinates of those points of inflection are. And so I've got 0 to the 4th minus 4 times 0 to the 3rd plus 2. So it's definitely just 2. And then 2 to the 4th minus 4 times 2 to the 3rd plus 2. So that's 16 minus 4 times 8 plus 2. So negative 16 plus 2 is negative 14. All right, so there's our point of inflection. So we are not going to work on this yet, but eventually what we're going to do is we're going to find the first derivative, find the increasing and decreasing intervals, find the maxes and mins, find the concave up, find the concave down, find the points of inflection. We could also find x-intercepts and y-intercepts if possible, and we could find asymptotes and stuff if possible. And then we're going to take all that information and we're going to use it to draw graphs by hand. So no calculators for these weird functions. We'll be able to do them by hand. So that's kind of what we're working towards right now. We're just doing it one piece at a time. All right, so here we're going to go ahead and write what the second derivative test actually says. All right, so the second derivative test says if the second derivative, f double prime of x, is continuous near c, and remember c was your critical number, so c is a number that either makes the first derivative equal 0 or it makes the first derivative undefined. So if the second derivative is continuous near c, then if the first, and that's what I was just saying, this is saying that c is a critical point. If the first derivative at c is 0 and the second derivative at c is greater than 0, so that means it's concave up, then the function f has a local min at c. So what we're saying, if something's concave up, then it looks like this. And saying that the derivative is 0 means that we're looking at the point where it has a slope of 0. And so it would make sense that that would have to be a relative min, right, or a local min. That's valid. And then the second part of that is if f prime of c equals 0, and the second derivative, f double prime of c, is less than 0, then f has a local max. At c. So again, if we think about this, we're looking at something that is concave down, and you're looking at the point on that where the derivative is 0, then yeah, it would make sense that that's going to be a max right there. Okay, so the first derivative test and the second derivative test both help you find local mins and local maxes. I'm going to be honest, I don't typically use the second derivative test because I have already figured out my local min and local max based off the first derivative test and looking at my increasing and decreasing intervals. But we still, even if we don't use the second derivative test, we're still going to have to use the second derivative at least to figure out what our concavity is. So it doesn't mean you won't find the second derivative. It just means this is almost like a backup test. If your first test didn't feel good, or if you want to get your answer two different ways and just make sure you got it right, then that's when you could use the second derivative test. Okay, so here's another example. We're just going to go through and find that information again. All right, so f of x equals e to the negative x squared over 2. And I'm going to go ahead and rewrite that. I don't like it when they write stuff as fractions like that. I would much rather have that 2 as a coefficient. So I'm going to write this as e to the negative 1/2 of x squared. And so now if I need to take the first derivative of that, then what I have is keep it the same times the derivative of the exponent. So the derivative of the exponent is I would take the 2 and multiply it by negative 1/2, and I'd get negative 1x to the positive 1. So if I fix that up a little bit, that's going to be negative x e to the negative 1/2 x squared. All right, and now I need to go ahead and find my second derivative. So if you wanted to use the second derivative test, you would still need to know what your critical points were. So we would need to take this and set it equal to 0 and find our critical points. Which I'm going to have us do that. I wasn't going to, but we just talked about the second derivative test, so why would we not do it? Okay, so I'm going to take this and set it equal to 0. And I'm going to go ahead and solve for x here. And you can kind of think of this like factors. You know, you have like, if you have the factored form of something and you had two sets of parentheses, you could set them both equal to 0 and solve them separately. So I'm going to go ahead and I've got two factors here. I have negative x, and that can equal 0. And I have e to the negative 1/2 x squared, and I can set that equal to 0. So this x is just divide a negative over, and I get x equals 0. And so that means that this is a critical point right here. I have a critical point at 0. Over here, if I was to try to solve for x, I would have to ln each side. So I'd get negative 1/2 x squared equals ln of 0. And ln of 0 is not defined, so there's no solution for that part right there. Okay, so I only have one critical number, and that's at 0. And we'll keep that in mind for when we finish out the second derivative test. Okay, so now we're going to go ahead and move on and look at the second derivative, which is going to have the product rule. So I have the first times the derivative of the second plus the second times the derivative of the first. All right, and I'm going to go ahead and just clean this up a little bit. So I have a negative x times a negative x, which makes a positive x squared. I don't need that parenthesis, so times e to the negative 1/2 x squared. And then that's going to be minus e to the negative 1/2 x squared. And I know that I'm going to be taking this second derivative and I'm going to set it equal to 0. So I'm going to go ahead and factor this to solve it. And what you'll notice is that you have a GCF of that e right there. It's in both terms. So e to the negative 1/2 x squared times x squared minus 1. And I already know that I can't solve this because we just tried, but I'm going to go ahead and set it equal to 0 and try to solve it anyway. And the reason I'm going to do that is because I want my notes to be complete, so that when my future self comes and looks back at these notes, I know exactly what I did. So set it equal to 0. This one over here you can set equal to 0 as well. And so for this one, I'm going to ln both sides. And I know that it's not going to work because that's undefined. And then over here, I can keep factoring that. I get x plus 1, x minus 1. And so x equals negative 1, x equals positive 1. So when I do when I do my sign chart to find the concavity and to find the point of inflection, well, I know my points of inflection, but when I use my sign chart to find my concavity, those are the numbers that I'm going to use. Okay, so when I plug these numbers in, I'm going to be plugging them in up here. I can't use, yeah, I wouldn't use just this part. We have to use the whole second derivative. So I'm going to use this part. I know that this is something to an exponent, and anything to an exponent is never going to equal 0. It's never going to equal a negative number. It's always going to equal something positive. Even if the exponent is negative, it would become a fraction. It wouldn't become negative. So I know that that first term is always going to be positive no matter what I plug in. So I'm going to go ahead and use negative 2. So I have a positive. Negative 2 squared is 4. 4 minus 1 is positive. I'll go ahead and use 0. That's always going to be positive. 0 squared minus 1 is negative. And then I'll go ahead and use 2. Again, that's always positive. 2 squared minus 1 is positive again. So that means that this graph is concave up from negative infinity to negative 1 and 1 to positive infinity. This graph is concave down from negative 1 to 1. And I'm going to go ahead and write my justifications. So this is because f double prime of x is greater than 0. And this is because f double prime of x is less than 0. Right? I have 2 points of inflection. I have negative 1 and positive 1, and I can go ahead and plug those back into the original function to see what my y-coordinate would be. So I have e to the negative of negative 1 squared divided by 2, and so that's going to be e to the negative 1/2, and you can leave that as e to the negative 1/2, or you could say 1 over e to the 1/2, and I'm going to go ahead and say 1 over square root of e. F of positive 1 would be e to the negative of positive 1 squared divided by 2, which again is e to the negative 1/2. Okay, so we have our points of inflection. We know that these are our points of inflection because the second derivative equals 0 exactly. And then if we look at this sign chart to see what happened at our critical number, if you guys recall, was 0. And 0 is between negative 1 and 1, and that was concave down. So if it was concave down, then that means that we had a relative max there. So I'm going to say a relative max, and that's at an x-coordinate of 0. If I plug in 0, I get e to the negative of 0 squared divided by 2, which is just e to the 0, and anything to the 0 is 1. So you have a relative max at the point 0, 1. The reasoning behind that is because f prime of x, I can use f prime of x equals 0, and f double prime of x is less than 0. So this would be our justification. When we're doing the AP exam, the sign chart, you can use it, but it cannot be your justification. You have to write your justification like this.